G'day YouTube, welcome to the A.E.R.O Hillbilly Enterprises. That's Aerophysics Engineering Research and Operations. Emergency notice to airmen. A N.O.T.A.M regarding the Boeing 737 Max-8 and how to deal with the Runaway robot MCAS. Maneuvering Characteristics Augmentation System, otherwise known as a software robot, a veritable gremlin within the system. Yesterday, I viewed blancolirio channel's analysis of the interim report into the Ethiopian Airlines crash of the Boeing 737 Max-8 in Ethiopia. And it's not a good story. I recommend that you go and look at blancolirio's video. Lowercase, one word, blancolirio channel, B-L-A-N-C-O-L-I-R-I-O. His name is Juan Brown. He's been flying for 40 years, US Air Force, 20 years with the airlines. He knows what he's talking about. He explained it so well, even I can understand it. Goes like this. When Boeing wanted to stick new engine technology onto a airliner, they could not see their way clear to paying the costs in certifying a whole new design. So they took an old design, they added the technology, and then when they discovered that the old design changed its handling characteristics in a very radical way, rather than admit that up front and retrain all the pilots of all of the 737 fleet to be able to deal with the characteristics of the 737 Max-8 and Max-9 or whatever they are, Boeing decided instead to come up with a software solution so that anytime the autopilot was switched off, anytime the flaps were fully retracted, if the aeroplane thought it was entering a steep nose up attitude, the software solution would remedy the situation by silently, unannounced, causing a nose down trim input. Here we're going to have to get a little tiny bit technical. When an aeroplane wing generates lift as it moves forward, some of the lift is by Bernoulli effect of the air going over the top of the front of the wing. Some of the lift is by Newtonian effect of the air being deflected downwards. People with PhDs are still arguing over which one is the dominant factor. However, what it means is that an aerofoil which is generating lift is also reacting to the down wash by pitching nose down. To control that nose down pitching moment, the Wright brothers put a couple of sticks in front of the wing, and they had a little tiny set of biplane wings that would lift the nose back up. That's what the aeronautical industry calls a canard design, because canard is a French word that means duck, and a duck has such a long neck that its head's so far out in front of the wing that it looks like the duck's wing is at the back of the contrivance. So an aeroplane which has its main wing at the back is called a canard. Everybody else decided to have the stick behind the wing and have a little horizontal stabilizer. So you have a great big wing at the front that's nose angles pitched up. You have a little tiny wing at the back on the end of a lever, and it's a stable dynamic instability. The difference in the angle between the nose of the front wing and the negative angle of attack of the nose of the rear wing is called décollage. It's a French word. French were very innovative in the early days of flying because they were the first people to buy aeroplanes from the Wright brothers. So anyway, your airliner typically has little elevators at the rear of the horizontal stabilizer. Those elevators are connected to the pilot's control yoke, and pulling back raises the elevators, which increases the down thrust on the tail, which raises the nose. However, you don't want to fly along, pulling 20 or 30 pounds to keep the nose where you want it on the horizon. So airliners also have horizontal stabilizer trim controls, and that means that the entire horizontal stabilizer, on which the elevator is mounted as a little flappy bit at the back, it's mounted around about its center of pressure on a hinge. The hinge allows it to move 10 degrees this way and 10 degrees that way from neutral, and that movement is controlled by a screw jack, i.e. a nut with a great big long threaded rod going through it. And there are two ways to move the nut and therefore cause the rod to move up and down through the nut. One of those ways is to use a little electric blip switch on the top of the control yoke. So you want the aeroplane to stop trying to dive into the ground, you pull back on the control yoke to get the aeroplane flying level, and then you blip, 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 blip on the switch. And what that does is it lowers the leading edge of the horizontal stabilizer, puts more downforce, raises the nose. You can trim it nose down as well. When you add power, particularly with the engines down below the wing, and the wings are under the aeroplane and all the drag's up on top, when you add power, that is going to push the nose up. So that's kind of what's going on with this MCAS system. It's designed to digitally make the aeroplane pretend that it's flying just like an old style version of the aeroplane, even though all of the geometry and the aerophysics has changed. And they didn't tell the pilots about this. But after the Indonesian Lion Air 737 Max-8 went into the water, and the pilots who'd flown it previous to the flight on which it crashed said they'd been having trouble fighting with the MCAS system and they barely got it back to the ground intact, Boeing did update all their manuals and everything, and they told the pilots what to do. However, here are your parameters. In Ethiopia, they were 13,000 feet above the ground, and they were only, 13,000 feet above the sea, and they were only 1,000 feet above the ground. When you fly at high speed, even though the nose might be pointing down, because of the curvature in the wing, you can still generate enough lift to maintain level flight. So the pilots in Ethiopia took off, they started to climb, they were on 94% thrust from their engines, that's rated maximum thrust for climb out. The auto throttle kept the engines at that setting all the way into the ground because they didn't want to slow down, because if they slowed down with such strong nose down trim, they might have dived into the ground. But that's getting ahead of the story. What happened was when they raised the flaps and engaged the autopilot, which engaging the autopilot should have negated the fact that raising the flaps switches the MCAS off, because having any flaps extended switches off the MCAS. Having the autopilot engaged switches off the MCAS. But the MCAS gets all of its data from one single angle of attack sensor vane. And when they switched on the autopilot, they switched on the left-hand autopilot, which was the same one that feeds the MCAS, and that sensor vane suggested that the aeroplane was 34 degrees nose up in the air. If it hadn't stalled, it should have. So the MCAS system pushed the nose down, and the pilots were looking at the airspeed, the horizon, the amount of air under their belly, and they're pulling as hard as they can on the control stick. And here's the other thing. When you're pulling on the control stick, if you haven't got access to the electric trim motor on the tail jack screw, then all you can do is wind a little wheel with a handle on it in the cockpit that has basically a winch and wires going back up there to the nut. When the nut is not under load, it's easy to turn. When you're pulling really hard on the elevators, loading up the tailplane, that nut gets really hard, and if you're going fast enough, you can't physically generate enough force on the hand wheel to turn the nut back at the tail. So these two blokes find themselves with the aeroplane trying to push down. They use the trim switch on top of the control yoke. And yes, the control yoke overrides the MCAS. But as soon as you let go of the control yoke, the MCAS kicks back in about 3 seconds later, maybe 5 seconds later. That's very important. These guys fought with it, played silly buggers, looked up the textbook. Both of them took a turn looking up the textbook. Both of them took a turn flying it, all within 6 minutes, happening in real time. And they came to the conclusion what they had to do was use the 2 switches at the bottom right-hand side of the central console, which the manual said that'll switch off the MCAS. They switched off the MCAS, and that depowered the jack screw at the tail. They didn't have any electrical control from their blip switch. So they were left with only the little crank wheels, and they were already going too fast for the crank wheels to be able to overpower the friction of the loaded up nut on the jack screw. So in desperation, one of them thought, well, maybe if we turn the MCAS back on, we'll get power to the electrical jack screw, and then we can retrim. And they did that, and it worked. But they did not think to immediately disable the MCAS as soon as they'd succeeded in getting the nose back up onto the horizon. And therefore, they left the bloody thing intact, continued trying to pull on the control yokes. The MCAS gave it eventually full nose down trim, and they were doing nearly 600 miles an hour in an aeroplane that's not supposed to ever go much faster than about 450 when they impacted the terrain. And Boeing is in such disfavour, they've had to ramp down the production of 737 Max-8s. But there are still 737 Max-8s out there right now flying cargo. They haven't all yet been grounded. So here's the point of this video. It seems to me that if you're stuck in the front end of a Boeing 737 Max-8 and you've just taken off and retracted the flaps, and all of a sudden the aeroplane starts to try and dive into the ground, the very first thing you should do is deploy 5 degrees of flaps. If you deploy 5 degrees of flaps, I swear to you, as an ultralight motor glider test pilot who limps following a crash which broke 1 foot in 1992, I swear to you, as somebody who knows what it's like to break an aeroplane, if you deploy 5 degrees of flaps at the first sign that the MCAS system is running out of control, because the autopilot will not remain engaged, because the autopilot has detected an error in the angle of attack sensor vane data, just deploy some flaps before the speed builds up, and you'll be fine. You'll be able to retrim the aeroplane, get everything set up for level flight, then switch off the MCAS and fly back home. Land it. Your other option, if you've already got too much speed to deploy the flaps because you're frightened you're going to tear them off the back end of the wing, switch the MCAS or leave the MCAS switched on, trim with your electric trim switch on top of the control yoke, get the nose where you want it on the horizon while holding the trim with the switch. Get your co-pilot to switch the MCAS off and disable the bloody thing before it has a chance to override you 3 to 5 seconds after you let go of your trim switch. The caveat is, I have only ever flown in an airliner, and that was in about 1983, and it was a turboprop Fokker F-27 Friendship. But what the heck? Lift equals weight. Thrust equals drag. Nose heavy aeroplanes fly badly. Tail heavy aeroplanes fly once. For whatever it's worth, my opinion is that Boeing should have entirely recertified the 737 Max-8 and Max-9 as a different aeroplane and simply taught all the pilots how to fly it, and ignore the bloody software half-assed digital secret squirrel solution. Simply tell the truth. Explain to the pilots how the aeroplane will really respond and teach them how to fly the thing rather than sitting them in the front treating them like mushrooms, keeping them in the dark and feeding them on bullshit. So if you're trying not to die in a Boeing 737-8, first deploy your flaps, and if you're too fast for that, coordinate your switches and disable the MCAS between trim inputs. Here endeth the notice to airmen. Warbles on a lot to YouTube. Ciao.